Let's start talking about uncertainty in measurements. All right, so now that we've talked about units, let's look at the values that go with the units and how we obtain them. Now, all measurements are going to have a limit to their certainty because the final digit in our measurement is going to be estimated. What that means is we can only write down so much information from a measurement. We can't continue to write out a long string of numbers simply because we want to. We're going to be limited at some point to how many numbers we can include, because at some point there's going to be some uncertainty to a value that we write down. All right, let's look at an example of this. We have two balances shown here, the analytical balance on the left, top loading balance on the right. The quality of these balances is going to be slightly different. We can see that the one on the left can give us up to 4 decimal places. The one on the right can give us up to 3 decimal places to our numeric value. In both instances, the last digit of their measurement is where we're going to be uncertain about that value. That's where uncertainty lies. And that's what limits us to 4 decimal places on the left, 3 on the right. So, for example, according to the analytical balance, the mass is 1.8290. But the 0 isn't completely certain. The true mass of whatever we're measuring could be 1.8291. That last digit is where the error is going to lie. And very important is the fact that the quality of our instrument is going to limit the number of significant figures in our measurement. So the analytical balance is a higher quality. It can get us 4 decimal places, which gives us more significant figures to our measurement. The top loading balance on the right is a little bit lower quality instrument, so we only get 3 decimal places, which only gives us 4 total significant digits. So let's look at a different example of this. If I were to ask you what is the length of the rectangle above the ruler, what would you say? Well, some people might estimate 1.5. Some people might say 1.6. Some would say 1.7. So, where do these disagree? In other words, what decimal place is there uncertainty in? Well, they disagree in the first decimal place. They disagree in the 5, 6, and 7. Right? Everybody agrees it's above 1. They just don't know how far above 1 is. So we're limited by our measuring device. And this is very important. You can only estimate 1 decimal place beyond the smallest division. So in looking at our ruler here, smallest division is in the ones place, so we can estimate to the tens place. In other words, we're uncertain about the tens place, but we've got a good enough measurement to really guess what that tens place would be. But that's where uncertainty lies. And we definitely wouldn't want to guess, for example, like 1.55 or 1.63 or 1.71, because we don't know enough about the measurement using our current ruler. So let's add a marking here. We're marking it at the halfway point. So from the guesses before, which is the better estimate of length now? Well, with the added marking at the halfway point, most of you are probably going to remove 1.5 because we can see it's actually above 1.5, and maybe 1.6 would be a better guess, or 1.7. Question is, what decimal place is there uncertainty in? Well, it's still in the tens place. Why not to another decimal place? Why can't we get it to the 1.65 or 1.75? Well, if we look at the smallest markings, even though we've added that halfway point, that's not actually adding additional markings enough to where we can estimate to another decimal point. All we can say is it's going to give us a slightly better or more accurate measurement of that rectangle, but we don't have enough markings to actually go to another decimal place. And this is where we're going to start to make a distinction between what we call accuracy and what we call precision. So the halfway markings allow more accuracy to the measurement, but not more precision. Alright, so let's add markings at the tens place. Okay, now we're adding in all those other markings besides just the halfway point. Now in looking at that length, we definitely know it's above 1.6 but below 1.7, so maybe we'd guess 1.62, 1.63, 1.64. So in this case, what decimal place is there uncertainty in? Well, now it's in the hundredths place. Right? Because we agree on the 1.6 part, it's the 2, 3, or 4 that we disagree. So the reason why we can get to that hundredths place now as our last significant digit in our measurement is because we have smaller markings. So remember, the last digit in a measurement is always where uncertainty lies, and it's always going to be limited by our measuring device. This is very, very important to remember, as it's going to lead us to how we determine how many significant figures to include in a measurement, because we can't write out however many numbers we want. We're always limited by our measurement. So remember, the last digit in a measurement is always where uncertainty lies, and that's always going to be limited by our measuring device. This is very, very important to remember, because it's going to lead us to how we determine how many significant figures to include in a measurement we take. All right, so in looking at all three together, we can see how that measuring device affects how many significant figures you can have in a measurement. If we look at the top ruler versus the bottom ruler, we can get more significant figures from a measurement with the bottom ruler because we have more markings. It's a higher quality measuring device. Keep in mind, you typically estimate one more decimal place beyond the smallest marking you have. And remember that even if you have like the halfway point marking, you need to have all the markings to have that additional decimal place. All that halfway point marking does is help improve a little bit more of your accuracy of your measurement. So keep this in mind when you're using these measurements based upon markings. All right, so let's test this out. What's the volume of the graduated cylinder on the right, of the liquid in there? Now remember that the numbers are increasing from bottom to top, and also make sure to read the value from the bottom of the meniscus. You need to make sure to think about how many significant digits should it have for the measurement. So I'll give you a couple of seconds here to think about an answer. So I would say the level is 4.59, but that 9 is where we're going to have uncertainty. And that 9 is where we're going to have the last significant digit we're going to write for our measurement. And it's the only value we have to estimate. I think everybody would agree it's 4.5 something, and you may have said 4.57, you may have said 4.58, you may have said 4.59. That's where we're in disagreement, and that's fine. So when doing measurements, you need to make sure to take into account what the smallest markings are, which is going to help you determine how many significant figures your measurement has. All right, so we talked about how those markings and how we do those measurements is going to help us lead to something called precision and accuracy. Let's look at those a little bit more closely. All right, with precision, precision is how close data is going to be clustered together, or how reproducible the measurements are. If you do the same measurement over and over again, do you get the same result each time, or close to the same result each time? We can use standard deviation to show this. Also keep in mind, precision is going to be determined based upon uncertainty in our measurements. Accuracy, on the other hand, is how close the data is to the true value. You may have to consider an average of results for accuracy. Right? Another thing that's going to affect this is its accuracy is going to be determined by how well the instrument has been calibrated. So, in looking at the darts on the boards, if the bullseye is the correct value, then in C, the far right, the darts are all close to the bullseye as well as to each other. So we'd expect them both to be accurate, they're close to the bullseye, and precise, they're close to each other. In B, the middle one, the darts are precise, they're grouped together, but they're inaccurate, they're away from the bullseye. And in A, the one on the left, the darts are imprecise, they're not close to each other, and you may say it's inaccurate. Now this is where it can get a little tricky. If we look at the central location between all the darts, that location is actually close to the bullseye, which would be accurate. So this brings up something we have to consider with these measurements. Although each measurement may be inaccurate, we will sometimes look at an average of values to consider for accuracy. So let's look at a numeric example of precision and accuracy. Suppose 3 students are asked to determine the mass of an object whose known mass is 10 grams. The results they report are listed here in this table. So for each student, we want to determine whether their results were accurate or precise. So to do this, let's look at student A. We know the known mass of the sample that they're measuring is 10 grams, 10.00 grams in fact. from their values, if we look at an average, they get an average value of 10.13. So, based upon that average, you compare it to the known, would we say that is an accurate mass? Well, it's not too far off, but it's still off from the known mass, so we'd probably say it's inaccurate. To determine precision, we'd look at standard deviation. The higher the standard deviation, the less precise the results are. In other words, what we'd say is more spread to the data, or the less clustered the data points are to each other, or less close they are to each other. And looking at this standard deviation, 0.3, we could probably say that's fairly imprecise. It's not very good precision, at least in comparison to student B and student C. Sometimes precision based upon standard deviation it's tough to call sometimes, and you always have to make that judgment call as to whether you're going to call it precise or not. So let's look at student B. Student B, the average was 9.79, not close to the 10, so inaccurate. But if we look at the standard deviation, it's a fairly low value, and we can see just by looking at the numbers they're fairly close to one another, so we'd say it's got good precision. Student C has an average of 10.01. Well, I would say that's pretty accurate because it's very close to the 10.00 grams. And looking at the standard deviation, 0.03, low standard deviation, good precision. So their results were accurate and precise. Now another way to look at this sometimes is to look at it graphically. And when we just have numbers without those averages and standard deviations, it's sometimes easier to see graphically the accuracy and precisions of these. So in looking at these graphs, and one thing to note is that the blue line is the line for the true mass of the object that they're measuring. We can see student A, their values are all over the place, so we know they're imprecise. Also, their average is above the true mass, so we know that their average is inaccurate. If you look at student B, it's easy to see that they're below the known mass, accepted mass, so they're going to be inaccurate, but their values are all close to one another, so they're going to be precise. And then student C, we can see average is really close to that blue line, so they've got accurate results, and all of those bars are roughly the same height, so they're precise as well. So we always want to be thinking about accuracy and precision in our measurements. Now, let's go back to the balances from before. We want to think about which one is going to be more precise, which one is going to be more accurate. So, precision is going to be determined in this case by the plus or minus values listed above. So the analytical balance is plus or minus 0.0001 grams. Top loading balance is plus or minus 0.001 grams. So the analytical balance typically is going to be more precise because it goes to the fourth decimal place, whereas the top loading balance only goes to the third decimal place, and that's where our error is at. Accuracy, on the other hand, is a little bit more difficult to determine from these. It's not a matter of how many significant figures we can get out. It really comes down to with our instrumentation. So with accuracy, it's going to be determined by whichever one is calibrated properly. Calibration with a balance involves taking objects with very exact and known masses, and you basically adjust the balance until they read that mass. If you have a balance that's not properly calibrated, you can get very inaccurate results even though they may be precise. So calibration is very important. Ideally though, whenever we're doing measurements, we'd still want to look at multiple measurements on each device to determine an average so we can determine a little bit more accurate value. Now when taking measurements, we've talked about uncertainty and where error is at, and that last significant digit is where we're uncertain, that's where the error is. Now we've talked in terms of instruments. We can also talk in terms of the errors themselves and the different types. So one type of error is called systematic, or sometimes called determinant, and that's where our values are either higher or lower than what we'd actually expect. This generally is caused by a consistent mistake in taking a reading due to either faulty equipment or a bad experimental design. Usually it can be corrected, and so you can reduce this error a lot of times. The other type is called random or indeterminate error. This is where the values are higher and lower than the actual, so it's random. Sometimes it's higher, sometimes it's lower. With systematic, it's either higher or lower. It's always in the same direction though. Now, with random or indeterminate error, a lot of times it depends on the measurer's skill in the equipment. Alright, there's other factors involved, but really because it's random, this error is always present. There's a lot of things that can lead to it. and it's very, very hard to remove. It's almost impossible to remove because no matter what measurement you do, there's always going to be some sort of random error associated with it. All right, so let's take another example of accuracy versus precision. So what I want you to do is take a minute and decide, are the burette measurements precise? And then, is the graduated cylinder accurate? So in looking at the burette measurements, they're all fairly close to each other, so I would say yes, they're precise. Now it'd be better to have a standard deviation calculated from those values to give us a better idea of that, but just in looking at them, they don't seem to be scattered too much beyond right around 26.5. In looking at the graduated cylinder being accurate, well, if the value of our measurement is 25 milliliters, then yes, it's accurate. However, if the value is closer to 26.5 milliliters, then no, it's not accurate. Sometimes it's difficult to know exactly which one is more accurate or more precise. And a good rule of thumb is that typically instruments that give more decimal places to the measurement tend to give more accurate results as well. They definitely give more precision, but accuracy generally improves with that as well. Once again, assuming the calibration is correct. So that's it for uncertainty in measurements.